Being recorded. Got it. So I guess maybe first, I just want to thank everyone for coming. We've been trying to put this together for a long time. Thanks to Woojin and Alex for doing all the work. Yeah, I think we have a good crowd, and I hope this starts a good discussion for the next weeks, months to come.
All right, so I guess I'm the chair of the first session, so feel free to start. Amit will be the first speaker this morning.
Okay. Okay, so I guess I'll just start. So my goal today is just I want to present a couple open problems. I think I have 4 or 5 about just generalized persistence diagrams. But first I want to start with a little review. I don't have anything technical, so but I do have citations, so you can look them up. So let me start with just a little background on these generalized persistence diagrams, and I'll quickly move to open problems. So persistence diagram. So here's one way of thinking about the persistence diagram. So the idea here is you start with some filtration of a space. So maybe you have a finite filtration K0 through Kn. And then what you do is you apply homology with, say, field coefficients. And then you get a bunch of vector spaces with arrows between them, linear maps between them. And then from this, we can define something called a persistence diagram, which I like to draw my persistence diagram like this. So if my filtration is, say, indexed from 0 to n, I list, well, I should have started at 0, from 0 to n on the x-axis, 0 to n on the y-axis. And for every interval, a less than or equal to b, we have a dot, and the dot has some multiplicity. And in the classical setting, one-dimensional filtration, field coefficients, all the dots are going to have non-negative coefficients. And here's the inclusion-exclusion way of calculating these multiplicities. So what you do is, if I want to know the multiplicity at this interval ij, I calculate the rank at ij minus the rank here, ij plus 1, plus the rank here, I minus 1, j plus 1, minus the rank here. And that gives me the multiplicity of this point. So that's one way of defining this persistence diagram. I like to call this the inclusion-exclusion way of thinking of it. But then you can also talk about indecomposables. So given a persistence module now, so it's let's just say some finite totally ordered post set in a functor into category of vector spaces. This object here decomposes very nicely into bars. And so we can define its persistence diagram as this list of indecomposables. And so one of the really cool things about classical persistence in this setting is that these two ways of thinking about the persistence diagram are equivalent. So when considering one parameter filtrations using coefficients in any field, these two very different ways, I think, of thinking about these things are the same. But things diverge when we ask, well, what about the multi-parameter setting? So not over filtration, not over a totally ordered post set, but something more general, like a lattice or an arbitrary post set. And what if we want to use coefficients in any ring, not just field coefficients? Right? And so we've had success in this area using the inclusion-exclusion way of thinking about this. So the big idea here is that inclusion-exclusion is a very special case of the Möbius inversion. So this is something I discovered while I was a postdoc at the IAS a while ago now. And so here's the idea of the Möbius inversion. This is definitely not the most general form of it, but this is the form that seems to be most, that's what we've been using in some of the papers I'll describe soon. So given a function, so here's what the Möbius inversion is. So suppose you're given some function f, and so p is any locally finite post set, and g, let's say, is some abelian group. Then there is a unique function, I'll call it partial f from p to g. such that for all P in our post set, f of P, we can recover f of P from this partial f in this way. So we look at all P prime that's less than or equal to P, and we just do a sum. And so that's the Möbius inversion. So this partial f, we say, is a Möbius inversion of f. And I put a partial here because you can think of this, you can think of the Möbius inversion as a derivative. It's a combinatorial derivative. Okay, so this classical persistence diagram using the inclusion exclusion formula. Well, inclusion exclusion is a special case of Möbius inversion being applied to a very special post set. Okay, so this then leads to several generalizations. I'm just going to go through a couple of them. So the first generalization of persistence, so the persistence diagram is, well, let's just still look at one parameter, but now we can vary the target categories. So instead of vector spaces, we can start looking at more general things. So the first thing is, say, some skeletally small symmetric monoidal category. Okay, so certainly category of vector spaces is one of these things. But for example, the category of sets, finite sets, is also one of these things. So if we're given any kind of functor like this, a persistence module, we can define this generalized persistence diagram. And what it does is assigns to every interval, just like ordinary persistence, it assigns to every interval a multiplicity. But now this multiplicity is no longer an integer, it's valued in the growth and decay group of this category. And so its generalized persistence diagram is a function defined as a Möbius inversion of the rank function. So the rank function is something like this, and you just take its Möbius inversion. And this turns out to be stable under something called under this weak distance I call the erosion distance. Generalization 2. Now suppose the target category, so it's still one parameter. Suppose the target category is abelian. So now it has more structure. It's not just symmetric monoidal, but it's abelian. We can define the generalized persistence diagram in the same way. It's a Möbius inversion of the rank function. But here on the right-hand side, I'm going to replace what I had in the last slide with the growth and decay group of an abelian category. So the idea here is we have relations in here that force every short exact sequence to split. So C is any abelian category. This can be really complicated, can have very complicated objects, but what this group does is forces every object to split into its primal components. And that's exactly what's needed to prove bottleneck stability. So in the abelian category setting, we have bottleneck stability, which is one of the main results for classical persistence. And then we can go even further. So here's some work by Pushka. What he does is now takes what we've done previously and looks at now functors like this, where P is now any locally finite post set and C is symmetric monoidal. And all of this goes through as well. And it's weak under, it's stable under the erosion distance, not bottleneck. Generalization 4. Similar setting. Here you have any locally finite post set and you have some general category on the right-hand side. And then it's work by Wujin and Facundo. They look at persistence diagrams of this form. So it's not just, they're not assigning intervals some element of the growth and decay group, but they're assigning connected, path connected components. They're looking at path connected components. So more general subsets of P, not just intervals. And this is all well defined as a persistence diagram, and it is stable. And then I think this last generalization I want to talk about is functoriality. And so this in my mind was a major, this was a big discovery because functoriality is something I've been looking for a very long time. And this is the first, this is first of its kind in persistent homology. And so here, what we did was we fixed some simplicial complex K, but that can be generalized. Let's just say you have a simplicial complex K, and we have a category now where the objects are filtrations of K over any finite lattice. And we say metric lattice too, because we want to talk about stability. So, the functoriality doesn't need metric, but we do need a metric to talk about stability. So the objects are this one, finite metric lattices with filtrations on them. And morphisms look like this. So suppose I have one object, one filtration, and a second filtration, G. A morphism from one to the other is a lattice map, alpha, from L to M. So L and M could be very different lattices, but a morphism is just a lattice map such that G is the left Kahn extension of F along alpha. Okay, and so this is the key idea here. So you can think of a left Kahn extension as some kind of is a deformation. I like to think of it at least that way, as a deformation from F to G along alpha. And so those are the morphisms. And on the right-hand side is our category of persistence diagrams. Let's call it DGM. And the objects look like this. They're intervals, so it's int L. So it was over all finite metric lattices L, and we look at intervals over L. So if I have a lattice L, its set of intervals is also a lattice. And so our persistence diagram, what they're going to do is assign to every interval a multiplicity. So in general, it's just going to do C. So the idea here is we're just going to do pH using field coefficients. And this can be generalized using previous ideas. Let's just stick to fields coefficients. So it turns out the growth and deep group of the category of vector spaces over any field is Z. So the objects look like this. Assigns the persistence diagram, which is the assignment to every interval and an integer. And a morphism looks like this. Suppose I have a persistence diagram sigma and a persistence diagram tau. A morphism is induced by a lattice map between L and M, such that this map is charge preserving. So the idea here is we have a persistence diagram sigma, persistence diagram tau, and the relation between them should preserve the charge. Meaning if I take any interval, M to M prime, in capital M, so that's in here, tau, the multiplicity that's assigned to this interval, is equal to the multiplicity of the preimage. So, right, so let's look at the preimage of this interval, which are a bunch of intervals in here. There could be many. So let's look at all I, let's look at all I in the preimage, and we do a sum. Take the sum of all the intervals in the preimage. Okay, so what's happening? So this is all M strictly less than M prime. So we're not looking at intervals on the diagonal. So that's important for stability. And it turns out that with this setup, the Möbius inversion is functorial. So there's a functor, pH star, that takes every object, every filtration to a generalized persistence diagram, every morphism to a charge preserving morphism. And now stability, we get a much stronger form of stability, we call it the edit distance. It's stronger than the bottleneck distance. And it's closely related to Gromov-Hausdorff. And it turns out just the proof is trivial. Everything follows from functoriality. Okay, so Alex will talk more about this in his talk next. Okay, so let me get to open problems now. So we have a nice area now of generalized persistence diagrams. There's still a bunch of stuff we need to work out. But we have stability. And now the big open question is if we need efficient algorithms. So here's one way to, so here's one question. So if I give you just a one parameter filtration, and I want to compute a generalized persistence diagram using non-field coefficients. How do I do that? So so that's an open problem. Let's what are some interesting non-field coefficients and how do we compute the generalized persistence diagram? And I have a paper coming out very soon with Greg Henselman. And we have an efficient algorithm for computing just 1D persistence using coefficients in finite abelian groups. But it'd be nice to consider more general coefficients. And I'll talk about another problem that uses more general coefficients. And then there's a multi-parameter problem. So given any finite lattice L and a filtration, compute a generalized persistence diagrams using just field coefficients. So just like a two parameter persistence. So L is just a 2-parameter lattice. How do we compute a generalized persistence diagram fast? And I've been working on this for a while. I have a paper with Dimitri. It's on the archive, but it's somehow not very satisfactory. So I think this is the biggest open problem in my mind right now. Just compute generalized persistence just for 2D filtrations. Problem 2. So now we have functoriality. What can we do with it? So here's maybe one way of using functoriality. So for example, consider a parameterized map. So M is a manifold, and we have smooth functions on F parameterized by Rn. And if this is this map is nice, let's say structurally stable, then there is a stratification on Rn, on the parameter space, such that suppose this is Rn and here's a stratification on it. And the stratification has the following property. If I take any 2 points, so any 2 functions, right? So 2 points in the parameter space correspond to 2 functions. If I take any 2 functions in the same stratum, they're going to be structurally equivalent. Structurally equivalent means that their sublevel set filtrations are going to be the same. Combinatorially, they're the same. And not only that, if I have 2 filtrations, say Q here and another one here in the lower stratum, the entrance path from one to the other is going to give a morphism between the 2 filtrations. And so what we end up getting is a co-sheaf. We have the entrance path category on the stratification with a functor into the category of filtrations on M. And then we can apply our pH functor to get persistence diagrams. So this gives us a co-sheaf of persistence diagrams. So now the question is, what can we study? What are some interesting invariants here? And I think this is related to the stuff Hans Ries and Rob Grice will talk about later. It'd be interesting to find some way. What are some interesting invariants? One of the problems here, which Tatum will talk about, is that these categories are not abelian, so we can't use stuff that's already out there. Okay, let's look at another problem. Homological inference. So one of the first applications of bottleneck stability, it's in the paper, the first paper, is inference. An inference looks something like this. So suppose you have some space X, the blue thing, maybe it's sitting in Euclidean space. And if the sampling is fine enough, then the stability of persistence diagram tells us that the distance function to the point cloud encodes the homology of F. So the persistence diagram of the distance function encodes the homology of X. So that's the details are in what's fine enough, and then the stability theorem. But now we have stability for the multi-parameter setting, stability for filtrations over any lattice. So this means we now have a way of handling outliers. And I think there are many proposals on how to actually do that, how to set up these filtrations to handle outliers. But I think it's time now that we should be thinking about this, a statement of stability now for statement of inference for sampling with outliers. What's the right setup here? I don't know. I think there are many ways of looking at this. Okay. Here's another problem, functoriality for persistence landscapes. So the persistence landscape of a filtration, so P is any locally finite poset, and K is some, let's just say some simplicial complex. Right, so there's work by, I think we'll hear about I think Parker will talk about this later. We can think about the persistence landscape as a Möbius inversion of its graded rank function. So I believe the functorial pipeline that Alex and I have should go through with persistence landscapes. And I think the idea here is to modify our pH functor so it gives a functor from the category of filtration to the category of graded persistence diagrams. And the idea here is to assign to every interval. So what we do is we assign to every interval its birth death. We call it the birth death function. So it's related to the rank function. But instead of assigning to every interval its birth death function, we can assign to it its graded birth death function, and then take its Möbius inversion. And so I believe that idea should go through. So we have to be careful on how to define its morphisms between such filtrations and morphisms between graded persistence diagrams. But it'd be nice to see a functorial definition of persistence landscapes. Now here's another open problem. So we're used to persistence over field coefficients, and so we're stuck in the world of vector spaces. But now we can do persistence with in an arbitrary Abelian category. We have bottleneck stability in Abelian categories. So here's maybe one problem to consider. So I'm going to set up here just one parameter persistence, not in vector spaces, but something more interesting. So let's consider the setting of Lyapunov functions. So suppose you have, so M is to say some space, let's say manifold, and suppose I have a discrete dynamical system on it. So a continuous map from M to itself, I'll call it phi. And then I have a height function on it too. And it satisfies the following axiom: for all real values R, if I take the R sublevel set, apply phi to it, and it's going to land in the sublevel set. And so what we end up with is a one parameter equivariant sublevel set filtration. So we have this, so we can filter M by the sublevel sets of F, but at the same time, for every sublevel set, so suppose C0 is a sublevel set. Oh, okay, maybe not C0. For every sublevel set, let's look at this. For every sublevel set, applying phi to it is going to give us something back in that same sublevel set. So we have the self map on every sublevel set, and it's equivariant, meaning if I take a sublevel set, go forward, and apply the self map, is the same thing applying the self map and then going forward. Okay, so now we have this equivariant filtration of M, and just apply homology with, let's use C complex coefficients just because it's algebraically closed. But there's room, you don't have to use C. C is nice. So let's say you have complex numbers, you apply homology with complex numbers. So what you end up with is a one parameter family of complex vector spaces. And in each vector space, you have the self map, you have an endomorphism. And everything commutes, meaning if I do this and then go forward, it's the same thing as going forward and then do the loop. And so this is a persistence module from a totally ordered post set into the category of endomorphisms on C. And this is an abelian category. So we can talk about a generalized persistence diagram, which assigns to every interval an element of the growth and deep group of this category. And so the growth and deep group of this category is really interesting. What it does is, so an object in this category is an endomorphism on a complex vector space. And such an object maps to, in its growth and deep group, its collection of eigenvalues. So the growth and deep group of an object, so the growth and deep group of this category is capturing eigenvalues of every object. And so what you end up with is a persistence diagram such that for every interval, you're going to get assigned to it a bunch of eigenvalues. Each eigenvalue could have some multiplicity. And then we know by bottleneck stability that Now, if I perturb this data, if I perturb this F, and if I perturb this phi in some controlled way, our bottleneck stability tells us that these eigenvalues are stable. Right, so, and I find this really fascinating. I don't know, I don't know what we can do with this, but this is it's very interesting. Like, eigenvalues are stable under bottleneck distance.
What do you mean by like this stability? Like we have a bunch of eigenvalues associated to interval, and could you explain a little bit more about?
Yeah.
Yeah.
So what ends up happening here is, okay, because we're still in 1D persistence, so I can try to draw its persistence diagram. Right? And so what happens is, for every interval here, what you're going to get is some set of eigenvalues. So, right, so it's a function from int p into the growth and deep group of the category of endomorphisms. And so for every interval, say this dot, we're going to get a bunch of, so let's say, yeah, and so this growth and deep, I believe, I forget now, this growth and deep group is the free abelian group generated by elements in your complex in C. And so what you're going to get here is you're going to get eigenvalues, and every eigenvalue will have a multiplicity assigned to it. And so every interval gets assigned. Maybe just keep it simple. Let's just say, well, yeah, keep it simple. Every interval gets assigned some eigenvalue with the multiplicity, possibly multiple eigenvalues with multiple multiplicities. And the idea is this thing is stable. So if I perturb my filtration a little bit, then I'm going to get a new persistence diagram. And bottleneck stability tells me that, okay, this one interval here may split up into two intervals. But the idea here is that if I take the sum of these eigenvalues, the sum is preserved. Right, so meaning if here I see 5 copies of some eigenvalue, I'm also going to see 5 copies nearby. It's possible those 5 copies split up. But it's the same idea as the bottleneck matching would do this, would match, would match, say, the 5 copies of your eigenvalue to, say, 3 copies here and 2 copies here. Right, so every interval gets assigned some eigenvalues, possible multiple multiplicities, and those eigenvalues are stable.
Can you match an eigenvalue to a, like, say, slightly different eigenvalue?
No, the eigenvalues themselves are stable. Like if this is 5, then I'm going to see a bunch of 5s here nearby. Right, which is weird. Yeah, okay, so that's all I have. I'm happy to go back and take any questions in the next few minutes.
Let's thank Amit. There are 2 people who raise their hands. I just suggest that you unmute yourself and go ahead. I think, Christ, you were first.
Thank you. And thank you, Amit, for a great talk full of all kinds of really cool ideas. My only comment is about your question at the end. What do those eigenvalues mean? Of course, I don't know, but I can't help but think that this has something to do with Conley index theory or Morse theory more broadly, because by Conley's theorem, you've got this Lyapunov function that works, but is constant along the chain recurrent connected components. And I feel that any sort of filtration associated with that these eigenvalues are going to be picking out sort of what's happening in the stable and unstable directions associated to those isolated blocks.
Oh,
That's my intuition.
yeah, yeah. Okay, yeah. The Conley index is very local, right? You take some subspace and then you quotient out outflow. And I see.
I see Bay has a question too. Please go ahead, Bay.
Yeah, hi, Amit. So quick question over problem number 3, where you talk about stratification of the domain.
Uh-huh.
Oh, that 2. Okay. So what do you really mean by finding interesting invariants? And what is example, in your opinion, to be something interesting, and what does that imply?
So for example, so if our Cauchys are valued in abelian categories, people study Cauchy homology. So that's a very interesting invariant of your Cauchy. And I think interesting in this, okay, we're not in an abelian setting, but I think something interesting would be like twisting behavior. So for example, like look at the pH transform. Suppose I have some shape in just the plane. I have some shape in the plane. I look at it as persistence diagrams in all directions. And it turns out you're going to get one of these sheaves, one of these Cauchys, because for most directions, the combinatorial filtration is not going to change. The combinatorial filtration only changes at some finite set of directions. So you're going to get one of these Cauchys. And so like, what can we pick out? Like what's interesting here? So I imagine there might be some interesting twisting behavior in the persistence diagrams on this pH transform. And so it'd be nice to pick out something like this, like, is there twisting behavior? And how do we identify it?
And so when you say twisting, you are really thinking about maybe in the setting of elevation function, the pairing switches when you change functions.
Stuff like that, right. So, right.
Okay.
So as you go around the circle, like you get these pairing switches, you come up, where you start out with some point in the persistence diagram, but maybe you come around to something else.
I see, but that then will be then related also the behavior of the vineyard as well, perhaps, hopefully.
Yeah, right.
Okay,
Yeah.
all right. Interesting to imagine, hard to make it concrete. But all right, thanks.
Uh-huh.
All right, I see that there are more questions, but in the interest of keeping the schedule, I suggest we switch to the next speaker. And perhaps a question can be asked offline
Between-
later.
Yeah, between talks.